the okay, I think we're good. Okay, so Johan, please tell us about breaking the one-line barrier.
Yeah, thanks a lot for the invitation. So as said in the introduction, I want to tell you about interactive theorem proving and how this has helped us in one particular project to break the one-line barrier. I'll explain that in more detail in the rest of this talk, and how we think that this might be a sort of methodology that can be applied in the future. So I'll start with the background story. On the 5th of December 2020, Peter Scholze posted a challenge online. Namely, the challenge was to check the main theorem of liquid vector spaces on a computer. And so there are maybe two things I want to say about this. So first of all, what does it mean to check a theorem on a computer, or maybe check the proof of this theorem on a computer? So like for decades, there has been software around that is able to understand mathematical definitions, theorems, proofs, and it can check these proofs down to the axioms of mathematics and flag when logical mistakes are made. Of course, to do this, all the definitions, all the theorems, and all the proofs have to be entered in a specific computer language. So there are several candidates for this. And so that's what we've done. And maybe the other thing to remark is that I'm Dutch, and the 5th of December is so-called Sinterklaas in the Netherlands. And that's a day on which everybody gives each other presents. So I took this challenge up as a present that Peter Scholze gave me on Sinterklaas of 2020. Right, so 9 days later, the following picture was posted on Twitter. And so these four guys are four musicians. They're the creme de la creme of progressive rock. And they form a band called the Liquid Tensor Experiment. And both Scholze and I are fans of this band. And so our project was named in homage to this band. So the history is as follows. In 1998, this band released their first album called the Liquid Tensor Experiment. 1 year later, they released Liquid Tensor Experiment 2. And by induction, you would expect that the next year they would release Liquid Tensor Experiment 3. But actually, there was radio silence for almost 2 decades, until on the 5th of December, Peter Scholze wrote this blog post called Liquid Tensor Experiment. And then 9 days later, they announced, okay, we'll do a third album. So this album was released last year on April 16. And this year on the 14th of July, we finished the formal verification of the proof of this main theorem of liquid vector spaces. So that's sort of, in a nutshell, what I've been busy with the last 2 years. And so today I want to reflect back on that. And I'm not going to tell you much about liquid vector spaces and all the mathematics, like the technical details of the mathematics involved, but I want to reflect on the sort of the social dynamics in our project, the way we worked, how technology helped us, and I think that's also in line with the theme of this seminar. So I want to talk about formal mathematics and how this helps with large collaborations, how it helps with managing the cognitive load of a researcher, a mathematician, how it helps with sort of spec-driven development, and I'll explain what I mean by that, and how it helps with getting confidence and trust in the mathematics that you're doing or that you're trying to understand, and how to have sort of evidence more in the like usual sense of the word, not in the sense of like proof, but more in the sense of evidence. Like more in the legal sense, maybe I should say. Okay, and yeah, please ask any questions either in the chat or just interrupt me. I'm happy to clarify things. So let's get started with large collaborations. So traditionally, mathematical research, I think, is dominated by really small collaborations. A lot of papers have only 1 or 2 authors, maybe 3 authors. And I think that covers maybe 80% of all papers out there. And in the last few decades, maybe 2-3 decades, we have witnessed some changes. So there have been several, like even 10 author papers appearing. And a very notable newcomer in the field are the polymath projects that Timothy Gowers and Terence Tao have been pushing, and several others, which are organized around weblogs. And so there is a lot of dynamic research going on by a lot of people on the internet. And then in the end, typically everything is bundled up into a traditional paper, but with a lot of authors. And so technology in general is facilitating large collaborations, like the aforementioned weblogs, but also weblogs, of course, that are not related to polymath projects in particular, but still discuss a lot of mathematics. And Math Overflow, I think, is a wonderful example of how a lot of large collaborations sort of happen or start, where a lot of people are working together. So when we talk about like formal mathematics and formalization projects, then there are several well-known examples of large collaborations. For example, the Veit-Thomson theorem, so the odd order theorem, was formalized in Coq, and this was done by a team of about 15 contributors. Then there was the FlySpec project, which formalized a proof of the Kepler conjecture in whole, and this was done with roughly 20 contributors. And so in the Liquid Tensor Experiment that I was involved in, there were, again, about 15 contributors. So I think it's fair to say that these projects naturally scale to a larger amount of contributors than we usually see in mathematical projects, and they easily cope with this scale as well. So I want to explain in a bit more detail which technology we used in the Liquid Tensor Experiment, because we didn't just use a proof checker. So first of all, there was Blueprint software developed by Patrick Massot, another person in the Lean community, which takes a LaTeX document together with some dedicated LaTeX macros that create links back and forth between LaTeX definition environments, theorem environments, etc., and the corresponding code in the Lean theorem prover that we used for this project. So using this Blueprint software, we also generated a dependency graph, and this dependency graph was a very useful way to track progress in the project. I'll demonstrate these in a second. And then finally, the proof checker was used, and this ensures correctness and compatibility. And so as a result of using these 3 pieces of software, contributors could very easily work on sub-projects that suit them well. And they don't need to understand the big picture. Of course, it can still be a goal to understand the big picture, but it's not really necessary. Even if you want to have like confidence, if you want to have the insurance that everything fits together, because the proof checker takes care of that. So let me show you what this looks like in practice. So let's see. Okay, here's the blueprint. So the Blueprint software. This is all generated from a usual LaTeX source. And yeah, so we can just open this part and jump to a random section. And as you can see, this okay, it takes a while to render the mathematics, but then this basically looks like a LaTeX document. And all these check marks mean that they have been formally verified. So if you hover over it, then you can click on this Lean icon, and there is a link. So you click that, and it takes you to the source code on GitHub. And so you could try to check that this statement corresponds to the statement that we just looked at. So this is document with all these cross references, and then there is this dependency graph. So we actually have two sections, and both of them generate their own graph. So let's look at this graph. And yeah, so this is a dependency graph, meaning, for example, that the main theorem depends on all these ingredients. And you sort of take the transitive reduction of the graph, otherwise there would be way too many edges. So all this graph is sort of human, like all the nodes and all the edges are human generated by adding data to this LaTeX document. And then, of course, some piece of software actually renders the graph. So here is actually the main theorem. This is the statement that we had to formalize. So it talks about having two real numbers, and then S needs to be a profinite set, whatever that may be. And V should be a p-Banach space, which is some sort of variant of Banach spaces that show up in functional analysis. Then there is this crazy gadget MP prime of S. And finally, the statement is that for all I greater or equal to 1, certain X groups in the category of condensed abelian groups have to vanish. Okay, so I'm not going to explain what this is, except that I'll say that it's brand new mathematics. And yeah, so you can follow this. You can click on lean over here, and it will take you to the lean statement. So it takes you to this file, which is a rather short file, but it imports everything else in the project. And here you can see, okay, again, we have like two real numbers.
Can you enlarge the font a bit, or?
I can, yeah, sure. So let me try to do that. Is this better?
That's great, yeah.
Okay. Yeah, so again, you see that P prime and P are assumed to be two real numbers that are greater or equal to 0. I mean, we include this for technical reasons because this is a very useful assumption in the rest of the project. But in this particular case, we actually assume that P prime is strictly greater than 0, and P prime is strictly less than P, and P is at most 1. And then again, we have this profinite set S and this p-Banach space V, and we the theorem then claims that for all I strictly greater than 0, the ith X group between this crazy object and V vanishes. So you can see that it sort of looks like the statement that we just saw in the blueprint software. Okay, and then there is like crazy, this proof is unreadable if you don't know how lean works, but at least the statement you can sort of parse. Okay, so especially like having this graph was very useful because now everything is green, but along the way, when we were working on the project, like parts of it were green because they were done, they were checked in lean, etc. And other parts were still white. And so it was very easy to see, okay, these parts are done, these parts are where people need to work. And especially in combination with the other graph, because that graph is quite a bit larger, that was a very useful way to keep track of progress and also for people to see, like to find for themselves, like which parts of the graph suit me well mathematically and where can I work on. Right, so that's about how this technology can help to facilitate large collaborations. And so here's a list of people that made substantial contributions, and then there are many others that also helped with all sorts of smaller contributions. Okay, so now I want to talk about how interactive theorem proving software can help with managing cognitive load. So I should say about that that there are differences between the process of finding, developing, creating a proof, where, I mean, that's a process that I completely don't understand. It's a pretty mysterious thing. And then, of course, there's checking and understanding a proof. And that's the main thing that we did in this project. and it was still an enormous challenge, I think. And of course, even though I don't really understand how to find a proof, like I don't have an algorithm for that, I still think that parts of what I'm going to say also apply to that. But like the main focus is on like checking a proof and understanding a proof. So cognitive load, when you're trying to understand a proof, first of all, arises just from raw proof complexity. If the proof is extremely complex, you can expect to have a large cognitive load. If the proof is very simple, then hopefully the cognitive load will not be so high. But then there are also other things that influence this. So you need to keep track of side conditions to lemmas. So if you're checking a proof and it applies a certain lemma, then you need to check that all sorts of rather trivial, like not just the main two conditions maybe, but also 3 side conditions need to be checked. And if there are lots of side conditions and if they're maybe unintuitive, that this can substantially increase the cognitive load. Then there might be discrepancies between statements and proofs. So it's a well-known phenomenon in mathematics that you write down a statement of a lemma and then you prove something, and maybe the proof actually proves something slightly stronger than the statement says. And then you can like still use that lemma, even though you use it in places where the statement isn't strong enough, but the proof is still strong enough. Okay, so this is of course somehow unfortunate, but it happens. And it doesn't like mean that there is a gap in the proof, but you need to spend some mental capacity on keeping track of this discrepancy and being aware of the fact that like there's no real mathematical problem. It's just that the statement should be formulated in a slightly stronger sense. And then, so like certain definitions or lemmas might need to be tweaked. Maybe someone will write, well, if you make this and this change to the following lemma statement in that and that paper, then the proof will still work verbatim, and we apply this tweaked lemma statement. And sometimes this is even applied to like 10 pages in a row. So then you suddenly need to keep track of, you sort of need to do some mental substitutions to 10 pages and checking, okay, if I make these substitutions to all the definitions and lemmas that occur in these 10 pages, does everything still work? And does it actually apply to the situation I'm looking at in the paper that I'm trying to understand? So formal mathematics does not really decrease this raw proof complexity that is just inherent to the mathematics that you're working with. But it certainly does take care of keeping track of these other things that I mentioned, like side conditions, discrepancies between statements and proofs, and tweaking definitions and lemmas. Because it's very easy, like the computer will just check these side conditions or remind you that you need to check them. And once you've checked them, you can forget about them. And if there are discrepancies between statements and proofs, then the computer will be unhappy about this. So you need to actually make the statement stronger. And you can easily do that by editing the lemma statement, and then the computer will make sure that now it actually aligns with what the proof does and with how you're trying to apply the lemma. And similarly, like if you want to say, well, just take these 10 pages and make these changes and then apply them, well, then you actually just copy paste those 10 pages of formally verified mathematics. You quickly make these changes, and then the computer checks that everything actually worked, and you can check that they apply in your situation. So yeah, it definitely keeps track of these extra contributors to cognitive load. So what is the result? The result is that now you can actually spend most of your mental RAM on the big picture, on this raw proof complexity. And whenever you're working on one particular lemma, well, then you can focus your mental RAM on the proof complexity of that lemma. But once you're done with that lemma, you just seal it off and your focus returns to the big picture, and you no longer need to worry like, okay, am I applying this lemma correctly, or do I need a slightly stronger version? Did the proof actually prove something slightly stronger, which is what I need now? Or like you can really rest and be assured that the proof checker said, okay, everything is fine, you're applying it correctly, and all the 10 side conditions that you needed to keep track of have been kept track of and are applied correctly or are satisfied, etc. And this is like in the liquid tensor experiment, this was a very important feature to us, because Scholze himself wrote that one key problem I had, so I'm quoting him, one key problem I had when I was trying to find this proof was that I was essentially unable to keep all the objects in my RAM. And I think the same problem occurs when trying to read the proof. And I can testify to that because I've made like 3 attempts to understand the pen and paper proof, just using pen and paper without a computer. This was all part of the process of the formal verification, because I tried to understand the big picture. I tried to understand the proof so that I knew better how to then transform it into a formally verified proof. But this just failed. And so Lean really was a proof assistant. So proof assistant is sometimes the terminology used for these kinds of software. And most of the time it sounds really preposterous to me, given the current state of the art in formal verification software. But in this case, it definitely applied, because it was very often the case that I just could only see 2 or 3 lines ahead on paper, and then I would basically get lost in how the structure of the argument worked. And so I would decide, okay, let me just enter these 2 or 3 lines into Lean. And then when I did that, I suddenly understood, okay, now I understand how the next 2 or 3 lines work. It's very similar to this experience that you might have when you try to read a text in a foreign language that you're not that familiar with. And if you just try to read the entire text in one go, you get lost halfway the page. But if you sit down with the dictionary and you translate the first 2 sentences into English or whatever, like your mother tongue or something, then you see, okay, but now I can make sense of the next 2 sentences. And this experience was very similar to what I experienced while translating this proof into Lean. And so, yeah, I could somehow see, okay, well, we certainly need this lemma. So let me just try to input that into Lean, or at least input the statement, and then maybe someone else can try to work on that proof. And then once that was done, we suddenly understood, okay, now we see what the next 2 or 3 steps are. Right, so that's how formal verification can really help with managing the cognitive load of a mathematical project and of a complex proof that you're trying to understand. So regarding spec-driven development, I claim that large projects can benefit a lot from top-down development. And what I mean by that is that you first write a skeleton of what you want to do, and you fill in the details later. And once again, the proof checker gives this assurance that everything fits together and becomes a coherent whole, and that you don't drift off into certain marshes where things become shaky and don't actually fit together. So what do I mean by that in more detail? What do I mean by that in practice? Well, certainly abstraction is one of the most powerful tools that we have in mathematics. And I think, yeah, under that terminology, the spec-driven development might actually already be quite familiar, but we can actually sort of make it quite precise using this formal verification software. So while creating a new definition, you should actually focus on writing down its main properties first. And so these main properties form the spec, which is short for specification, or maybe in computer science lingo, you would call that the API. And it's really important that you test these properties in practice. Like, do they actually form the correct abstraction? So you need to, I mean, you're making this definition with a certain purpose. You want to prove a certain theorem. And for that, you need certain mathematical objects. Okay, so you create a definition. And so it's important to sort of work in two directions. You need to show that this definition captures the sort of mathematical objects that you're interested in, but also that the theorem that you want to prove is actually valid for these abstract objects that you've been defining. And I claim that it's maybe better and easier to first check that that they form the correct abstraction, that they allow you to prove the theorem that you're defining, before focusing too much on filling in all the details required to show that that the objects you're interested in are examples of this definition, for example. So in particular, you can work out many details later. Certainly if you're quasi-confident in the mathematical theory you're working in. And collaborators can also very easily join there. So how did it work out in practice in the liquid tensor experiment? Well, we had to, at some point there is this very technical tool being used called a Green-Delin resolution. And so Green-Delin resolutions haven't been used that much in mathematics, but they've been around for a while. And to show the existence of a Green-Delin resolution requires an enormous amount of algebraic topology. So if we would have done a bottom-up approach, then we would know, okay, at some point we need these Green-Delin resolutions, but to show they exist relies on a lot of algebraic topology. Okay, so let's first build a whole library of algebraic topology so that we can get to these Green-Delin resolutions and then build on top of that. Instead, we just wrote down the properties of Green-Delin resolutions that we needed. And once we had this list of properties that we needed, we discovered a much easier object with similar behavior. And so this is now actually like a piece of new mathematics that was discovered along the way that will actually also be useful in just pen and paper mathematics outside of the liquid tensor experiment. And I claim that this was a very strong example of like first writing down the spec of what you need, first write down the specifications. And once you have that, then you can start filling in the details and maybe you find a much easier path. And so more generally, many key statements were written down without proofs and with only stubbing out the definitions that went into the key statements. Sometimes even the definitions were like partly just asserted without actually giving them in detail. And before embarking on like the large and complex proofs that went into this project, it was still very cheap to tweak the definitions and statements. So by doing this process of first writing down the statements and sort of the large scale skeleton and the specification of how things needed to behave, we could try to get that right, and it was very cheap to tweak things before actually embarking on proving things. Once you've proven something, if you want to change it, then the proof might have gone to waste, or at least you need to fix parts where the proof break, etc., etc. And so it becomes a lot more expensive to like make these changes. And I think that's another benefit of this spec-driven development. Like changing the spec, if you only have the spec, changing the spec is really easy and cheap. And so once the dust settled and we had all these main statements and definitions in place, then work on the proof could also easily be distributed, and many people could start working on filling in different gaps in different places. Right, so finally I want to talk about confidence, trust, and evidence. and how formal mathematics can help there. So, I mean, before we started on this project, the situation was sort of as follows. There was this really complex proof of a brand new piece of mathematics. And this main theorem of liquid vector spaces is a wonderful black box. You don't need to understand the proof, you only need to understand the statement. And then you can apply this statement in many different places. And that's also the main reason why Clausen and Scholze were so excited about it. It bundles an enormous amount of complexity into one proof, and then you can apply this theorem in many different places as a very powerful machine. And to apply the machine, you don't need to understand how the theorem was proven. So they've actually shown how to use this to simplify proofs of a lot of classical theorems in complex geometry, which used to have extremely hard proofs, and now they have really elementary proofs, I would say, apart from the fact that these elementary proofs rely on this one big main theorem of liquid vector spaces. But if you're willing to accept it as a black box, well, that's great. Then you now have an elementary proof. And but yeah, how do you get confidence in the fact that this theorem is proven correctly? Well, first of all, you can of course be very confident because it was proven by a Fields medalist. So that helps a lot. And you can try to understand it yourself, but as we just saw, I mean, it barely fits in your RAM, and it's really hard to understand this proof. Okay, so you can ask for a formal verification of the proof like Scholze did, but then how do you believe in machine-checked proof? This was a question that Pollack asked himself in 1997, and he wrote a very interesting interesting paper under this title. So the title is How to Believe in Machine-Checked Proof. And so the main things he points out is, well, you would need to trust the hardware and the software, first of all, because, I mean, if there are bugs in your hardware, then they might absolutely not do what the software is trying to do. And if there are bugs in the software, then, well, maybe your proof checker like says, well, this is a correct proof, but actually it isn't. So you need to trust those. And I claim that these problems are basically solved by now. Like, there might be things wrong, but the chances are extremely small, and it's not something, certainly not something that a mathematician should really worry about. I mean, there are people that worry about this, and that's really good because they're like working on the final problems here. But yeah, for the working mathematician, this is not where the problem is. The problem is, how do you trust the formal statement? How do you know that the statement that we wrote down in Lean actually matches what is written on paper? And right, so from now on, I'll just assume that we trust the hardware and the software. And I already showed you what the formal statement looks like in Lean, and also what it looked like in the sort of LaTeX version, or at least this HTML rendered version of the LaTeX document. And they sort of looked quite similar. But, well, how can a casual observer actually gain real confidence that the following three align? So first of all, there's your mental model that you have of mathematics. Then there might be a pen and paper representation of mathematics. And finally, there might be this formally verified representation of mathematics. And it, like, there are different ways to approach this depending on your background. For example, if you're the author of a proof, then your mental model of mathematics is sort of the ground truth, because like you came up with this mathematics, you found it, you discovered it, you created it, and then you tried to, as faithfully as you could, put this into pen and paper mathematics by writing an article or something, or you try to put it into a formally verified representation. But your mental model of mathematics is ground truth. On the other hand, if someone else wrote a paper, then basically, well, you don't have access to their mental model. Only via the pen and paper representation can you sort of try to access it. And so that becomes the ground truth, basically. And you need to make sure that your mental model aligns with what is written on pen and paper, which is what we usually understand by the process of like reading the paper, trying to understand what's written there, etc. And then there might be this third component, this formally verified representation. So actually, I think this became quite clear during discussions that we had after the liquid tensor product was completed, that this question of gaining confidence and trust in, for example, the formal verification in the liquid tensor experiment is very different for Peter Scholze and for other mathematicians, because Scholze has this mental model of what he's trying to prove, and that is his ground truth. And so he wants to know whether what we did matches his mental model, instead of trying to check that what we did matches what is written on pen and paper. So I'm going to ignore how Scholze can get confidence, or can get more confidence in what we did than a casual observer. So I'm just going to provide evidence that the pen and paper representation of the mathematics aligns with the formally verified representation of mathematics. And somehow this will pass through the mental model that a casual observer has. But the mental model is maybe not the ground truth, at least not for the main statement. Right. Anyway, this is a long story. But if the statement is really easy, then there is actually a pretty easy answer. For example, Fermat's last theorem has a tremendously complicated proof, but the statement is really easy. It's just a very short statement about natural numbers, and natural numbers are one of the easiest definitions that you have. So you just check all the definitions. You check the definition of natural number, you check the definition of addition, multiplication, raising a number to the power of another number, and well, then basically you're done. So you can very easily check that a formal statement of Fermat's last theorem in some formal proof checking software matches your mental model of what Fermat's last theorem should look like. And then maybe if you're somewhat paranoid, you should actually also check the notations, because does the notation for addition actually match the definition of addition of the natural numbers? Because typically this will just be some function called nat.add or something like that for addition of the natural numbers. And the plus symbol will be a piece of notation for that. So you need to check that the notations actually match. And then, okay, it might look like Fermat's last theorem, but if you're really, really paranoid, you should maybe also check, like, did the people writing this formalization do something really evil with, like, Unicode characters? Maybe they used 0 with Unicode characters that you cannot see, but they're still there. Or maybe they used, like, a crazy alphabet, like maybe they borrowed a letter from the Cyrillic alphabet that means something completely different compared to the usual ASCII character that looks the same. So, okay, if you're really, really paranoid, you need to do things like that. But maybe just checking all the definitions is good enough, and also something you can actually do in practice. On the other hand, the main statement in the liquid tensor experiment relies on thousands of definitions. So the main statement, like on the surface area, covers real numbers, profinite sets, p-Banach spaces, condensed abelian groups, derived functors, like these X groups are an example of derived functors, etc. But recursively, these definitions rely on many other concepts, from homological algebra, category theory, topos theory, analysis, etc., topology. So if you like need to check those definitions to see if they match your mental model, or to see if they match what's written down on paper, then you also recursively need to check that those definitions are made in terms of definitions that also match what's written down on paper or match your mental model. And well, that quickly becomes impractical if recursively it relies on so many definitions. And you might at some point truncate the work that you need to do. You might say, okay, well, I certainly believe that the real numbers were done right because so many people have looked at those definitions. I trust the community that they got this right. Okay, so maybe the thousands of definitions, you don't need to check all of them, but you might still need to check like several hundreds of definitions. And the main statement also relies on pretty complicated notation to hide several functions and parameters that are completely irrelevant. Like you wouldn't write them down on paper. You might be applying a functor to certain objects, but to apply a functor to certain objects, you need to turn it into a function on objects, and like to turn a functor into a function, you need to apply a function to the functor, etc. It quickly becomes annoying and complicated, and so you use notation to hide that. Okay, so once we're using notation, are we using the notation correctly? And are we not like abusing notation in like maybe not even in an evil way? Maybe it was not intentional, but maybe we just messed up. And then finally, and this might actually be evil, like 0 with Unicode characters show up in our project, not in the main statement, luckily, but there are several intermediate statements that rely on 0 with Unicode characters to transparently trigger some automation that was needed to keep the statement readable. Okay, so if we do that, you might want to make sure that the main statement actually doesn't also do something evil with 0 with Unicode characters. Well, this quickly becomes pretty horrible and annoying. And I think maybe, so the best way to approach this is using abductive reasoning, or more informally known as just apply the duck test. So if something looks like a duck, it swims like a duck and quacks like a duck, then it probably is a duck. And so the way we did this in the Liquid Tensor Experiment is that we created an examples folder with 5 files. And each of these files focuses on one object that occurs in the main statement. We make sure that these files stay short, that they're really well documented and readable, even for someone who doesn't have any experience with the lean theorem prover. And they should exhibit the standard behavior of the object. So in some sense, this ties back to spec-driven development. These documents should exhibit the spec of the object under question. And in this way, show that all the objects swim, walk, and quack the way they should, so that someone can be convinced and gain evidence, not in this extremely precise formal mathematical way, but more in the colloquial way of the word evidence, that these objects actually match what is their mental model. So I can, yes?
Could you be a little more specific? Are these instances that satisfy axioms? Are these like
no, I can show you
proofs, or what are
so here we have this folder online, the examples folder. And so, for example, I can go to the file on real numbers, and so we load in the exact same imports that were loaded in on the file that contained the main statement. So that means that we aren't cheating with like other definitions. We're using the exact same definitions as in the main statement, and we open all these pieces of notation, so we are using the exact same notation, etc. And then this file just says, okay, we show that the real numbers are a conditionally complete linearly ordered field. So basically this boils down to this statement that, I mean, it's a linearly ordered field, it's Archimedean and it's complete. And so if you have any other such condition, like linearly ordered field, then the two are isomorphic. And in fact, the isomorphism is unique. So if you have any two such isomorphisms, then the two isomorphisms are equal. So this is creating evidence that the real numbers in Lean are really like unique up to isomorphism. And okay, if you're curious, then you can like look up what the definition is of this thing to show that it's actually talking about linearly ordered fields, etc. But I mean, it creates a first layer of evidence that it behaves the way
I'm
it
not
should.
quite, I mean, these are proven statements or they're not proven statements?
Yeah, this is all completely formally
So when you say,
verified.
well, so when you say evidence, I mean, proof is very strong evidence. In what sense is it lacking?
Well, I mean, maybe conditionally complete linearly ordered field is a sort of vacuous statement. You would have to look up what the definition is of this claim, this predicate.
But the sort of what we're supposed to take is that there's an example of a conditionally complete linear ordered field, or that
Yeah, I mean,
it's
it says that this symbol, which is the symbol for
real.
what is called the real numbers in also in Lean, it satisfies this predicate.
Right.
Okay, but what is this predicate? Well, you'd have to look it up. But I mean, it exists in the main library, and so it depends on your level of like paranoia, how far you want to go. Like you could easily claim that this doesn't provide any formal evidence at all, because I didn't tell you what this means. But it looks like what something that matches something in your mental model. And
but these are statements that are not strictly required to make the proof, but that are provided to convince the reader and the user.
Exactly.
Yeah.
So for example, like this was a very, very short example. So maybe let's look at the example of profinite sets. So this says, okay, let's take X a profinite set. Well, then a profinite set is a compact Hausdorff totally disconnected topological space. If like, I mean, profinite sets are not like they're all over the place in certain parts of mathematics, but maybe not in all parts. But like if you happen to work in number theory or in algebraic geometry or something like that, then you know what a profinite set is. And so this matches something that is in your mental model. And then here, these lines of Lean code say, well, whenever X is a profinite set, there is a topology on X. And actually, it's a compact space. And actually, it's a T2 space, also known as Hausdorff. And it's a totally disconnected space. Again, like maybe totally disconnected space is true for all X if we just messed up that definition. But so that depends again on your level of paranoia. Do you want to check this definition? Or do you say, well, this looks very reasonable to me. I think that profinite probably behaves the way it should behave. Well, I mean, maybe we define profinite to just be a predicate saying that X is a one-point space. Well, the one-point space certainly satisfies all these claims. So we might want to check that we didn't do that. Okay, well, whenever you have an X that has a topology, it's compact, T2, and totally disconnected, then we can actually turn it into an object of the category of profinite sets using this construction. So indeed, it quacks like the duck. It quacks the way it should quack. And then we start like checking that homomorphisms in the category of profinite sets are actually just continuous maps from X to Y. Then we start doing like Grothendieck topologies and sheaves. I'll not go into the mathematical details, but
But
So-
I think we see the point. These are
Right,
all statements that are not in the main line of the proof, but certainly.
exactly. I mean,
Expected.
the
properties.
main
Um,
the main theorem claims that certain X groups vanish. Well, maybe we defined X groups to be the zero group, just always, then the proof would be completely trivial. So in this file x.lean, I think towards the end, we actually compute the x1 of z modulo nz with itself to show that not all X groups are zero. Like, I mean, maybe the stronger evidence is that we show that X is a universal delta functor. If that's something that makes sense to you, then probably you will regard that as a strong evidence that we didn't mess up the definition of X. And so here is this claim that the X1 of z modulo n and z modulo n equals z modulo n. Right, so that's sort of the point I wanted to make. This, in the end, this is, if you want to be 100% sure that we got everything right, then you need to check thousands of definitions. But if you want sort of circumstantial evidence that we didn't mess up anything and didn't do anything evil with notation, then here are 5 short files that have pretty readable statements. And together they provide evidence that all the objects behave the way they should behave. Right. So in conclusion, I'm claiming that formal mathematics helps with managing large collaborations and managing cognitive load. It helps with like making spec-driven development precise and scaling that up so that you can, this is very closely related to large collaborations, so that you can like distribute work over many contributors, and it helps with gaining confidence and trust in complicated results and complicated proofs. Yeah, thanks for your attention.
Thank you. Are there questions from the audience?
I have a question.
Yeah. Can people hear?
Yeah.
So maybe you should come up to the.
So first of all, it's a really nice talk, and congratulations on the accomplishment. I'm curious, and it's a question that's not like strictly in line with what you've been speaking about, but I'm curious if you think that formal mathematics could play a role in doing things like making, say, refereeing math papers more straightforward, where a referee wouldn't have to read through a computation which, you know, is in principle doable by a human, but instead you could have a paper which is just regular math paper, and at one point say this particular lemma for the proof referred to the attached lean code. And I guess I'm wondering how far away you think we are from that, if you think that's a goal.
Yeah, so I would say it's certainly a goal. I also think it depends very much on, like, whether it's already sort of within reach now, depends very much on what kind of computation and which area of mathematics you're talking about. Like, whenever you want to do something in the Langlands program or something like that, well, that's very far out of reach. But for example, there's a really nice example. So Thomas Bloom solved a conjecture by Erdős last year, and there was a really nice Quanta article about this. And half a year later, he had a completely formal verification of his proof. And so actually now there is a formal verification of his entire proof, even before the paper that he had submitted was fully refereed.
Did he do this verification himself, or?
He did it himself together with one other person from the Lean community. Yeah. But I mean, this was a conjecture by others, so you can sort of like it was something in like combinatorics / analytic number theory, but the analytic number theory was I don't mean this in a demeaning way, but it was elementary in the sense that you needed clever arguments, you needed like really creative arguments in combinatorics, but you don't need a lot of huge machinery from analytic number theory. And so all the prerequisites were already available. Of course, you can black box some of the prerequisites, but then again, the referee will have to judge whether you set up your black boxes correctly. And so in that sense, I think this last part that I was talking about with the like how you gain confidence and trust, I think that's a technique that could be used a lot, so that referees need to check that the ingredients match their mental models, and then they only need to check, like they need to check this for all the ingredients in the statement, and then they can have trust in the proof. They can outsource that to formal verification software. So yeah, I think there are plenty of applications, and how much you can do right now, I think that's still limited. It might require a lot of effort. Like it took us 1.5 years to work through the entire proof that Scholze had written, together with like all the prerequisites, because of course, like we needed an enormous amount of topos theory and homological algebra that Scholze did not write up because he just assumed it. But it wasn't done in lean, so we had to do that. Yeah, and of course, like not every paper will find a team of 12 people willing to work on parts of that paper to formally verify it. So, but that's something that I hope, and I think there's good reason to hope that it will become easier in the next 1 or 2 decades. And so then this might really become feasible.
Thanks. I'll ask for one more question. Just to add, can you estimate the number of man years that was spent on this verification project?
Right. So I think Adam Topaz and I both basically worked on this full time. So that would be 2 times 1.5 years. And then many other people spent like a couple of months or several weeks on it. So I think I would estimate like around 6 years.
Okay, good.
Yeah.
Okay, maybe we have time for one more question. There's another question from the audience.
Can I ask a question?
Well, I'm going to let maybe we have one more. Eric, go ahead.
Oh, thank you. So this is really fascinating. Are there obstacles that you see to applying the tools that you used to applied mathematics, for example, the study of partial differential equations?
I mean, so are you thinking more in the direction of like numerical modeling and things like that? Or
it could be new methods, or it could be applying, solving PDEs that you think are a good model in some complicated situation.
Right. So I think like if you're trying to, there are several things you can do. So if you're trying to just, I mean, there's sort of theoretical numerical methods where you're like saying, okay, I only took one course in numerical methods. So there is the Runge-Kutta 4 algorithm, and I'm going to prove formally that this algorithm actually does what it claims to do. So that would be very similar to what we did in this project. Another thing is that you say, okay, I'm just going to implement this algorithm on a computer, and then run it, and then you might still want to so do you want to run the algorithm, or do you only want to prove theorems about it? If you want to run it, then you might still want to know that you implemented it completely correctly, without bugs creeping in that might like make rounding errors or something like that. And so that's certainly another application. And I mean, for example, Intel had this really nasty bug in the Pentium processor a long time ago, and they had to recall a whole bunch of processors because like the hardware was just not doing what it claimed to do. And so they are formally verifying that all the logical gates on their chips follow the specification of the processor, so that it does what it should do. I mean, in cryptography, people are checking that cryptographic algorithms are implemented the way the specification says they should be. And in numerical methods, I mean, there are examples of really expensive accidents happening because of mistakes in numerical modeling, like the space shuttle or some oil drilling platform in Norway that like collapsed and cost millions of dollars and things like that. So having formally verified implementations of numerical modeling software could save lots of money, I think. And I know that people are working on this. So not me in particular, but yeah, that's certainly, does this answer your question?
Well, I guess I was just worried that maybe when you get into analysis, that some of the tools, but you've got Banach spaces out the wazoo, so maybe you're just fine. That there's no real domain obstacle to the kind of methods.
No, I mean, so I can point to one other project that's currently in the final stages. So there at the moment there is a formal verification of sphere recursion, that you can turn a sphere inside out smoothly without like tearing it up or. So I mean that is sort of something that typically would involve lots of pictures and intuition, etc., and a lot of hardcore analysis. And this is completely formally verified.
Yeah.
Yeah. So that's certainly possible. There's no problem there.
Eric, there's I've actually thought some about the sort of question you're asking. We should talk about it later. I'll take a question from our audience.
Yeah, hi. So yeah, congratulations once again. So I have a more like, I guess a programming type of question. So you mentioned that like in math, when people prove, like, you have statements, but then in some sense people use the proof more than the statement itself, right? Maybe like the technique in the proof or the construction. And then you mentioned that in this top-down approach, you kind of want to like, you just want to have statements, right? And you want to link them all together. And then like it's the API or whatever. And then you can implement however you want, right? But the API is where kind of everything else uses. So I was just wondering, like, first of all, in Lean, is it like really like you can put everything in a black box and like the proof in some sense doesn't leak? You can just use like the statement itself and link them together, and everything kind of just works. Like yeah. Does that make sense?
Yeah, I mean that's certainly like in a very strict sense in Lean, you cannot refer to a proof from another proof. Like if you're working inside a proof of lemma X, then you cannot refer to the proof of lemma Y. You can only refer to the statement of lemma Y.
Right.
Okay. So you're forced to write your statements correctly.
Yep.
And not say, well, the proof of lemma Y actually proves something stronger, and that's what I want to use now. That's not possible. If you're in such a situation, you need to go back and strengthen the statement of lemma Y.
Right.
Yeah.
So, yeah. Thank you. So my last question would be just like, but this, I guess in my mind, I feel like there's kind of a duality. So on one hand, if you think about computer programming, like you really just want to use other people's packages, so the statements. On the other hand, when you're doing math, you kind of want to know the methods, right? And that in some sense lies in the proof. So how does that, like, they kind of go contradict with each other in some sense, right? So I wonder, how does that really work, I guess? Or do you have anything to say about that?
Yeah, so I mean, I agree that that's a very important part of doing mathematics, is like trying to understand proofs. And that's also, in some sense, what we were trying to do here. And but my claim is that if you try to understand this proof, you would do well to first try to understand this big skeleton, like the specs and the APIs that we set up.
Yes.
And then the implementation details, certainly for a first, attempt at understanding it shouldn't really matter.
Right.
And then when you're interested in like more details, then you can start looking under the hood.
Yeah.
I like the way it is right now. I certainly wouldn't recommend looking at the lean code directly. I would very much do it in tandem with this blueprint software and the cross references from this like HTML web page generated from LaTeX. I would start with that. I would try to understand that, use this dependency graph to understand the big structure. And yeah, and then like, if you're familiar with lean and lean code, then you can start looking under the hood, because like a lot of the files are absolutely not readable. Certainly not the way these example files were readable.
Yeah, thank you so
Yeah.
much. Thank you.
Okay, great, thanks. Okay, so let's I'll thank Johan again for a really very impressive talk and accomplishment. And so next week we'll have, not next week, next week we will have a gap in the schedule, but on the 28th, we will have Surya Ganguly from Stanford talk about aspects of data and machine learning. So I hope to see you all there, and thanks again.
Yeah, thanks a lot as well. Bye-bye.
Bye-bye.